הרצאת הפתיחה של הכנס תינתן על ידי פרופסור יניק דסקטה, נשיא סוכנות החלל הצרפתית כנס. פרופסור דסקטה פעל ופועל להעצמת כוחה של כנס כמקור מרכזי לקידום היתרונות הטכנולוגיים והתחרותיים של צרפת ואירופה בקהילת החלל העולמית. מטרותיו העיקריות הינן לקדם את מערכות החלל העתידיות לשימוש המדע וטכנולוגיות יצירתיות לטובת האנושות כולה. מעל הכל, פרופסור דסקטה הוא ידיד, תומך ועוזר לקהילת החלל הישראלי ולמדינת ישראל. כבוד רב הוא לי להזמין את פרופסור יניק דסקטה, ראש סוכנות החלל הצרפתית כנס, להרצות בפנינו על עתיד חקר החלל. בבקשה.
Mr. Minister Ashkovich, ladies and gentlemen, dear colleagues, dear friends, good morning to all of you. First of all, I want to tell how much CNES and myself are honored and proud to have been invited for this keynote lecture today to the 7th Ilan Ramon International Space Conference. So I try not to be too long, and this lecture was intended to speak about future of space research, which is of course a huge subject, as huge as space, and I chose just to present some of our main ideas, views for France and Europe for the future of space, and especially in the scientific field. To go quickly at the beginning, all of us here know that space is everywhere. We use it everywhere. We use it so much that we depend actually on it now. And this now is much more well-known by the general public. Before, the space was distant, was a complex feature reserved to scientists. Now, space is in our daily life. And also, for the scientists, now space is giving us information about the universe that we cannot have on Earth, and it gives us information on our planet that will be absolutely necessary for our future. And the reason is, for this last point, is that if we want to know the functioning of our planet, we need to have continuous information of all the planets at the same time, and only satellites can do that. And the other point I will develop is about applications. Now we have came out of the technology push, and we entered in the market pool period, and now we are able to design the satellites, instruments, and payload corresponding exactly to what we need. So a lot of applications are now emerging. So a few words about the French space policy in the European framework. It's very easy. We want to master space, so we want to be able to access to space, and we want to be able to utilize all the space possibilities. So we want an independent and autonomous access to space. So we need rockets. We have Ariane 5 for the heavy lift. We have now Soyuz at the CNES center in French Guiana, Space Center, and in a few days we shall have, so Soyuz is a medium launcher, and we shall have the light launcher Vega in a few days. And of course, you need also space base to launch, and this is Kourou. But we are already thinking about the future, of course, and we have begun to study Ariane 6. It's a new launcher, which is not entirely defined today. We called it Ariane 6 because we lack a little bit of imagination. And the main characteristics will be reliability, of course. It's a modular launcher, being able to launch from 2 tons to 8 tons in GTO, and it will be designed to reduce cost, not to increase performance. What now is the main driver is the reduction of cost. And I want to also present this slide, this last bullet point. I mean, we want autonomous access to space for the utilizations of space. We think that we don't need independent access to space for exploration, because we deeply think that exploration has to be an international program worldwide with all the space nations. So we need to be interdependent, and we need to have a common space transportation policy. So about the utilizations, 4 strategic domains that everybody knows: telecommunication and navigation, everything about our planet monitoring, Earth observation, oceanography, meteorology, cartography, all the resources. Also the space science, universe science, exploration, and security and defense. And our strategy is to be present in all those 4 domains, or 5 domains if I add the access to space. But we know that space is a competition. Of course, it's huge cooperation. Space is international, but it is a competition. And the leader of the competition, the US, they are investing in public funding 6 times more than all Europe together. So the strategy must take into account this figure. And so the strategy that we developed to stay in the competition with respect to a leader much more powerful is the following. First, a niche strategy. So we want to be in the 4 or 5 domains, and we select only strategic positions, and we put all the efforts necessary to be at the first rank in those positions, and we don't spread the efforts. We concentrate. And we, of course, look for a strategy of excellence, meaning that we try to have the most innovative and fertile topics and ideas, and we have a very severe selection process for the projects. We need a cooperation strategy, because you cannot be the best in every field, and if you want to progress, you need to work with close partners who are better than you. And of course, it's also very useful because you can share the costs. And at last, we need a technical and industrial strategy, because, of course, we need industry to do all that, and we need to maintain a sound and competitive industry and competences. About now applications and services, I shall go quickly. I just wanted to say that it's important to keep in mind that investment in space infrastructure is very rewarding. If we look at the figures, which are published figures, the gear effect is 20. In fact, it is more than 20, and it is increasing. This is the lever effect. If you divide the revenues of the whole value chain, telecommunications, imagery, positioning, and navigation, just to the investment, meaning the satellites and the launch to put them in orbit, with each euro invested in the infrastructures, you inject more than 20 euros in the economy through the value chain, and this is increasing. Of course, for the radio communications, we all know now that we use satellites for all applications, and for instance, we are now working on the very broadband internet satellites, all the applications about navigation and data collection, and this open on a lot of applications beginning by telemedicine, tele-education, and so on. Same for Earth observation, where you can use imagery for a lot. Just think about Google Earth, for instance, but also all the applications for meteorology, oceanography, and so on. These are the first images of our Pleiad satellite, which was launched recently and worked very well at the first time. Now I come to scientific research. It's well known that the space observatories being outside atmosphere are giving a lot of data in wavelengths that we cannot have correctly on the surface of the Earth. And also we have those probes, those robots going on the planets to explore our environment, our universe. And also we have all those satellites which are taking a lot of measurements on physical, chemical data of our Earth. And of course, what we discover more and more is that our planet Earth system is very, very, very complex. All the ocean, atmosphere, continental surfaces, ices, interior, and so on are interacting in very complex manner, and we have a lot of work if we want to understand how it works and how to manage it for the future. And this is urgent because of all the climate issues which are developing quickly. So we know also that the human activities play an increasing role, perturbing and disturbing all this mechanism. And so if we want to understand, we must do science, meaning we must observe, we must measure, and we must make models. We must make science in order to understand. And it is complex because we have different time scales, but also we have different scales, the global one, the regional one, but we need also to go to the local one. And of course, the satellites are tools that are necessary. Of course, we need also the in situ devices, measurements, but we cannot do it without the satellites. Just a few examples about the oceans. As you know, we have opened a new field of science with NASA using ocean altimetry with the family Topex Poseidon, and then Jason 1, Jason 2. They are doing well, and we are preparing Jason 3, and we are already preparing the follow-on, I will explain. And this gave huge results, completely new science field, very fertile, about the knowledge of ocean, but also opening for the meteorology to seasonal forecasts. Here you see this increase of the level of the oceans, 3 millimeters per year, but we can also have information at the regional scale, but we can also now have more and more powerful and precise models about ocean dynamics, and this is very promising if we want to go also to the local scale. For instance, I put on this slide the fact that for the tsunami in Indonesia in 2004, as a matter of fact, Jason 1 was over this region at that time, and he could measure the two waves going towards India at that time, 50 centimeters high. Of course, nothing could be done with that, but clearly with those kind of tools, it's possible to monitor the planet and to have the necessary systems for warning, for early warning. And just this example to show that, because we have also other researchers about earthquakes and so on, this is very promising for the forecasts. Here you see the data about the El Nino phenomena, which is important because it's the beginning of those kind of predictions and warnings that we can give observing this, how to say this, huge bubble of hot water in the Pacific Ocean, giving floods on one side and dryness on the other, and vice versa. And this is the follow-on, which is the new generation, which is the breakthrough, now utilizing interferometry that we continue to do with our friends of NASA. It's called SWOT. And this is very interesting because it will give a much better resolution for oceanography, especially for the coastline, but also for the small scales. But it will give also access to the knowledge of the water, continental water, which is very important because those data are lacking. We don't know the inventory of fresh water, surface water, and its evolution on the surface of our planet. And with this satellite, for the first time we shall have the knowledge, and we shall be able to manage water, which of course is a huge stake for the future and even for the present of our planet. Now, after the ocean, the atmosphere, greenhouse gas effects, as CO2, which is already done by GOSAT, but we need more. There is OCO2 by NASA. We are working on CarbonSat or microcarb. We shall do one, we have to choose between those two missions. We are doing with DLR, Germany, Merlin, about the methane, atmospheric methane, by a leader. It's called Merlin. And also we have two satellites in the A-train with NASA in Canada. Those satellites are very close to each other, very close, so they are passing at the same time over the same zones, taking different measurements. So it's a very powerful tool to scan our planet all the time. And this, of course, gives very important and useful data if we want to understand and model our planet. So Aqua, Aura, Parasol, which is a CNES Microsat, Calypso, CNES Minisat, CloudSat, and soon GCOM and OCO. Just a few words about the scientific and operational missions. Of course, it's not the same specifications, but of course, the two fields are communicating. And I just give an instance about those EUMETSAT, which is a European meteorological satellite organization. The Polar Orbit METOP satellites. On board, we have developed a sounder called YASI. It's an infrared sounder. And just to say that, of course, it was it's a scientific instrument, but it gives for the metaphysics data which put in the numerical models, constraining them, made that the reliability of the forecast at the 6th day was the same as the 5th day. So we gain one more day, just with one instrument, one more day for the meteorological forecast. This shows how powerful those space tools can be for our daily life and understanding of our planet. Now, space science. Of course, those observatories outside the atmosphere are delivering extraordinary information about the violent universe and the cold universe. And some people say that Hubble telescope gave information to man on the universe in 20 or more years, more than ever before, since man is looking at the sky. So, of course, it's an image, but it shows the power of those instruments. The last bullet point is just there to quote that for space science, we have organized our research on the ESA scientific program. And as you know, maybe in ESA is responsible for the mission, but the payload is selected by the scientists, by the selection, and the instruments are bought in kind by the national agencies. And this is our priority. Just to quote the ESA Integral SPI telescope, and also the Planck telescope, and also Herschel, which are giving extraordinary results. Now, the Graal that we are all looking for is those dark matter and dark energy missing, and this will be the subject of international next missions, but these are very huge and difficult and costly missions which are in preparation. Space is a subject for research, but space is also a tool for research. Itself, it is an instrument for research, especially for microgravity, of course. And we have prepared microsat called microscope. It's also a Myriad family, CNES Myriad family satellite. It will be launched in 2016, called microscope. It is intended to check the Einstein equivalence principle. And I think it's very interesting to see that we can tackle such important subjects, which could be a revolution of our physics, with a micro satellite of a few tens of millions euros. This also shows the power of those space science and space instruments. We have also developed the Pharaoh clock, which is called Atom's clock to fly on the ACES experiment on ISS. And we also quote the ESA Gaia mission and Bepi Colombo as examples. And now a few words about the emergence of life, which is obviously very, very important Graal also for science. The reason, that's the main reason where for the French scientists, Mars is the top priority. More than any other, this is the reason. Mars was warm and humid at the beginning, and now it's no more. So something happened, and I think we all think that it is very important to know what happened. It's the next planet. And by the way, it's because of that, life could have appeared, and we have to know if it appeared on Mars or not. And by the way, it's also the next planet, so the planet where it seems possible to go with a man mission. We know that water was on Mars. I quoted here the measurements made by the Omega satellites, the Omega instrument on Mars Express satellite. And also, of course, it's interesting to look at other missions, especially asteroids or comets or other places, to give information about the relics of the formation of the solar system, but also because we need to train and to validate, develop technologies for this future human mission to Mars. And also, we need those probes exploring the other planets, the giant planets, and their satellites. As you know, Huygens could land on Titan, delivering a lot of information about this planet where water is replaced by methane, but it's raining and you have oceans and rivers of methane. And also, we have to look outside our solar system and find exoplanets, planets around other stars, and especially not giant planets, there are a lot, but planets which could have life on it. Telluric planets, and not too close, not too distant to their sun. And the first super Earth exoplanet was discovered by CNES satellite Corot, which is also a small satellite, launched in 2006, and which found this Corot Exo 7b planet. Since then, a lot of exoplanets, Earth-like planets have been found, and this is very interesting, but difficult to know if life could be on or is in those planets. So imagination tells us that we could have those kind of constellation or formation flying satellites, like the concept Darwin, in order to detect the signature of biological activity on planets. And this, I showed that slide only to remind that our technology is not able to do that, and so we have a huge work to do to find breakthroughs, technological breakthroughs, like formation flying, but also in the energy field and in the propulsion field, if we want to be able to do that and to give life to our ideas and to our dreams. Life science in space. It's very interesting to study the biology, animal, vegetal biology, but also medicine in microgravity in order to preserve crew health. But we can also have excellent, important results about medicine using microgravity experiments. And also for materials being free from gravity, give you access to the real physical phenomena without any disturbance from the gravity. And so a lot of important results are published by all those researchers, especially in the ISS or sounding rockets or other means. And those results can also be useful for applications on Earth, of course. Now a few words about exploration, and I will have finished. This is a quotation of what was voted in the Europe Space Council in 2008 about exploration. So you can read the sentence. The idea behind that is that exploration is not only scientific, it's a political endeavor and it's also a global endeavor. It has to be undertaken by all the space nations in a worldwide program. And which is very important here is to try to reflect all together and to find the right governance for such a program. Because it's easy to say that, but it's rather difficult after that to manage it if you don't have the right governance. It's a huge program, a long-lasting program. So the question of the governance is also important, and it has to be, according to us, a political governance associating in some interdependence all the nations with the objective, which could be to go for manned mission to Mars. So we looked at what Europe could bring to such an association, to such a program, and of course each should bring what he does best. And our ideas are around automation and robotics, energy production and storage, advanced propulsions, life support systems. And also this gives applications on Earth. And about that, we are proposing to develop some, multiple application device which could be autonomous for navigations, to go to a rendezvous with another object, cooperative or not cooperative, and to dock, because we need that for all the missions, for in-orbit assembling, for the space trains, for the servicing, for also removing the debris, and also to capture the sample returns for Mars, for instance. After the ExoMars mission, we are on board on the Mars Surface Laboratory, which will be on Mars next August with our instrument ChemCam, and the next one should be Mars sample return, because this is important about this question of exobiology, to have those sample return. And for this, we need to capture the samples around Mars. So this shows that this international program could include those kind of building blocks that we could share and then prepare this program in the optimal way. This is now my conclusion. Space is very young. It's only about 50 years. Which is very important is that the utilizations have really increased very much. I'm sure that we consume space today. Sometimes we don't know. Some people are using space and they don't know. But I think that this consumption will grow and grow, and space will be more and more present and useful in our daily life. We have obtained extraordinary progress in science, which is very important for our planet. And the last bullet point is important in my view, because as these applications are emerging and multiplying, some kind of different organization has to be put in place. Because up to now, the agencies were doing all the work, and they were going from one generation to the other. So we never had the necessity to ensure the continuity of data by funding recurrent infrastructure. For us, for instance, CNES, this emerges with the JSON, because after Topex Poseidon, JSON 1, JSON 2, there was JSON 3. And for instance, JSON 3 will not be funded by CNES. We have said that we will not fund it because we want to do SWOT. And in the meantime, we have done Altica with India in K-band. Because if we do that, all the money, all the the R&D money will go on the recurrent infrastructures, which is not possible because somebody has to prepare the future. And so we have to find another way to guarantee the continuity of the data and to fund the recurrent infrastructures. Because if we don't do that, nobody will invest in the applications and services. If somebody wants to invest and develop services for customers, he needs to be sure that the data will come and will not be shut down at the end of the life of the satellite delivering the data. So it means that we have to find the business model, and for us, the users, or the one representing the users, have to fund the recurrency. And for instance, JSON 3 is funded by EUMETSAT, mainly, for the European part. And this is the last slide. It seems to me that, by the way, we celebrated the 50th anniversary of CNES last December. And this was the opportunity to look in the past and to try to draw some lessons from the past. And what is really striking for me is that space is really unique. I've never seen a domain of activity, of science, of industry, a domain which is at the same time highly strategic for the states. It's a question of sovereignty, which is highly useful in our daily life. We use a GPS to come here, and by the way, it did not take us at the right place. But it's very, very useful in our daily life. We consume it all the time. It has a huge lever effect in economy. That's with an enormous return on investment for those infrastructure, more than 20. It is absolutely indispensable for science. It is indispensable to protect life on Earth. And above all, which is absolutely extraordinary, it makes us dream. And maybe it's one of the last dreams that human beings can have. And we all know that no human being escapes to that dream. We see that each time we make exhibitions or presentations. We all dream about that. And those dreams are very... for instance, I dream for the exploration of our universe. So the satellites are the Christopher Columbus of the future. And we dream also to those friends around us, ange gardien in French, guardian angel, I think, which are indispensable to give us the information in order to be able to go on living on this planet, to keep life on this planet. And that's why we say that space is the future of humankind. Thank you very much for your attention.
Thank you very much. Talking about dream We'd like to present you with our dream.
Oh, thank you.
Is space, science and technology for a peaceful world. It's a silver dove on a piece of rock from Jerusalem. Thank you very, very much.
Thank you very much. Thank you very much. Thank you.
ההרצאה הבאה תינתן על ידי דוקטור פיט וורדן. דוקטור פיט וורדן הוא ידיד ותיק, וזו לו הפעם השנייה שהוא משתתף בכנס שלנו, בראשות צוות מכובד של מרכז נאסא איימס. וורדן שירת 29 שנים בחיל האוויר האמריקאי ופרש בדרגת בריגדיר גנרל. בתפקידו הנוכחי אחראי וורדן על מרכז מחקר מרכזי של נאסא, המורכב מצוות של 2,500 עובדי מדינה וקבלני משנה, ואחראי על תקציב שנתי של $800 מיליון. תפקיד נאסא איימס לאפשר לנאסא ולסוכנויות האירונאוטיקה של ארצות הברית לבצע את משימותיהם בחלל בעזרת תמיכת מאמצי המחקר והפיתוח שהמרכז מעניק להם. וורדן יזם ודחף את תוכנית גרין ספייס, אשר בין השאר הביאה לשימוש ביכולות של מרכז איימס בתחום החישה מרחוק, לתרום לשיפור משמעותי בתחום בטיחות הטיסה האזרחית, לחימה בשריפות יער וביצוע מעקבים על שינויי אקלים כדור הארץ. וורדן שימש כפרופסור מחקר באוניברסיטת אריזונה ומוכר כמומחה בינלאומי בנושאי חלל אזרחיים וצבאיים. דוקטור וורדן ירצה בפנינו על החיפוש אחר חיים ביקום. דוקטור וורדן, בבקשה.
Minister Hershkowitz, Rona Ramon, distinguished guest and colleagues, first like to bring you greetings from NASA Administrator Charlie Bolden, who couldn't be here this year. He was able to address this group 2 years ago, and he wishes all of you the very best in your conference and your space future. But what I would like to talk about today is the future, particularly focusing on what we think is one of the most important areas in our future space endeavors, not only in the United States but around the world, and that's the search for life in the universe. One of the areas of research that has gotten very exciting is what we call astrobiology. And this is what I want to talk about today. And there are some critical questions. How did life begin? And where else is there life? Is it inside the solar system at other places than Earth, like Mars, or is it elsewhere? But this leads to perhaps the most important question of all. What is the future of life in the universe? And we believe that this is perhaps the primary purpose for our human exploration programs, and we think it's going to generate new and exciting technologies, and I'll talk about some of those. Now, in the last century, we developed aerospace technologies, developed rockets. Space travel began. The Apollo program succeeded in human footsteps on the moon. We have explored just about every planet in the solar system, at least with preliminary flybys, and we have done very great science in many different areas. But I would like to maintain that we're entering a new era, an era where not just aerospace technologies but biology becomes very important. Now, I put this American scientist picture up because, first of all, he's working with us, but some of his discoveries are beginning to show us a very interesting new future, and one that is potentially very important for science and for exploration. This is J. Craig Venter. A little over a year and a half ago, Dr. Venter and his team made the first artificial bacterial genome. This meant that they built up the genetic sequence, the DNA, using the very basic amino acids, and they constructed an artificial genome. Now, they used a template of an existing bacteria, and they were able to boot it up much as a computer program and to have it reproduce. This is the first of an incredible new era where we'll be able to actually program biology as we do computers. I believe this, coupled with aerospace engineering is what will truly carry us into the solar system and beyond. Well, let me talk about the search for life in the universe, because much of our research program focuses on this effort. This is the planet Mars. Now, for the last several hundred years, Mars was the subject of much discussion of was there life on Mars. Indeed, over a century ago, very famous science fiction authors like H.G. Wells assumed there was life on Mars. And in fact, in the 1930s, there was a radio show that read H.G. Wells, but many Americans thought it was real and hid in their cellars because they thought there were invasion by Martians. So for many years, we thought Mars might be the abode of life. But then in the 1970s, we landed on Mars, and we found it looked like this. Now, I went to school in Tucson, Arizona, and I thought this looked very lifelike because it looked like Arizona desert. But most of the scientists concluded that Mars was lifeless, that it was a dry desert and had no chance of life at that point. However, and since then, we have gotten a different understanding of Mars. We are finding that Mars has much water. We can see glaciers. For example, these are some of the Mars orbital photographs. Several years ago, we landed a small probe in the northern regions of Mars, and we dug just a few centimeters below the surface, and we found actual evidence of ice just below the surface. In fact, we think there is so much water on Mars that if it was all melted, it would form an ocean several hundred meters thick. This is a very interesting thing because we know that at least for Earth life, water is one of the essential components. We have taken pictures of cliffs and craters on Mars. This is a very recent picture. The flow patterns you can see at the bottom of this picture are very recent, that there is apparently water flowing underneath the surface of Mars even today. We launched just several months ago the Mars Science Laboratory, the Curiosity rover. This will land on Mars this summer, and it may be the first probe that will actually give us some evidence if life ever existed on Mars or may still exist. Very exciting era in science. We think that underground on Mars there may be flowing rivers and large aquifers, areas that contain much water. This is really a change in our understanding of that planet. And these may actually have life. We find evidence of not large-scale magnetic fields like the Earth, but small-scale magnetic fields on Mars that may indicate there are volcanic and other tectonic activity still going on Mars that would heat just below the surface. So these are very exciting possibilities. Indeed, there is some very tenuous evidence. This is a discovery made by one of my sister centers, the NASA Goddard Research Center, where they have seen variable methane on Mars. Now, methane on Earth is taken as evidence of life. In fact, most methane in the Earth's atmosphere, I understand, is produced by cows. Now, we don't believe that this indicates that there are cows on Mars, but there may be microbes that are producing variable methane. Now, I want to caution that my own scientists at NASA Ames think that the Goddard result is wrong. So there's a lot of discussion and discovery, and this is what science is all about. But this is a very tantalizing potential evidence of life on Mars. Now, there are other places in the solar system that we believe could hold life. This is one of the moons of Jupiter, Europa. Europa is heated by its orbit around Jupiter causes gravitational effects to actually heat the interior. We now believe that Europa has an ocean that covers the entire planet or moon that is perhaps tens or hundreds of kilometers deep, And what we see on the surface is an ice layer, and beneath that ice could well be conditions that where life could exist or arise. So there is much discussion of can we send probes to Europa and find evidence of life or eventually figure out how to get through the ice. There are other places in the solar system that have water, again, something we think is essential for life. This is one of the inner moons of Saturn, Enceladus. The Cassini probe, an international probe, has been watching Enceladus and the other moons of Saturn. And a few years ago, it discovered there were water jets that indicated that the interior of this object is actually warm enough that can produce water and spray it out into space. So Enceladus is another place to look for life. Now, there are other places that have fluids, not water. This is the moon of Titan, as mentioned by my French colleague. There are lakes on this object. This is a very large moon. It's larger than our moon. These lakes, though, are not made of water. They are made of hydrocarbons, either methane or ethane, but they're quite large. Now, the interesting thing is that there are proposals that strange life, alien life, that doesn't use water could exist there. This is a scientific paper by one of my colleagues at NASA Ames that actually believes that there are evidence of some of the chemistry of this moon that could be explained by very alien life. So there's possibilities, not only life as we know it, but truly strange life in the universe. Now, our solar system is just one of what we now know to be billions in our galaxy. Indeed, recent discoveries made by various instruments, including this mission, which is a NASA mission, the Kepler mission, are indicating that virtually every star in the or in the galaxy has a planetary system. And we are finding a very exciting new area of research on exoplanets. And this is just beginning. As was mentioned with the Corot mission, the only way we can see planets the size of the Earth is if the planet passes in front of the star and causes a very small decrease in the light level, an eclipse. But we are now seeing thousands, if not tens of thousands of these things. The Kepler mission is looking at a region of space that has about 150,000 stars like the Sun. We're watching the light levels very, very precisely. We can measure the light levels to 30 parts per million, and we are finding literally thousands, if not tens of thousands of planets. Some of these are Earth-size, and some of them are in the habitable zone. The habitable zone is defined as a planet that is at the right distance from its star that liquid water could exist on the surface. So we're looking for objects that would be like the Earth, that would have life like the Earth. The interesting thing, however, and I've given some of my scientists a hard time, is that when we actually study this, we find the Earth is not in the habitable zone of the Sun. It's actually outside it. So we're going to have to change this definition somewhat. The Earth should be completely frozen, but there's greenhouse gas effects. And as I said, we have found now at least 50 planets in the habitable zone. We do not yet have one exactly the size of the Earth in a habitable zone around a star like the Sun, but we have several candidates. We hope in the next year or two to be able to confirm that there really are planets the size of the Earth. Now, these kind of studies are beginning to make science fiction concepts real. And I would like to talk about science fiction because it has shown many of us in the science community the possibilities of the future. And one of the exciting things about it being a scientist is showing that that could be real. Now, this is not a NASA picture. This came from Lucasfilms. Those of you who are science fiction fans would probably recognize this is from the Avatar movie. But we are looking at some of the data that we are taking from Kepler. And in this case, you had a giant planet in the habitable zone that had a moon that was habitable and indeed was inhabited. So one of the exciting things about Kepler is we think we might be able to find evidence of not just Earth-sized planets, but Earth-sized moons in the habitable zones. So we're beginning to see science fiction could be real. Now, more recently, we have gotten some very exciting discoveries that also remind us of science fiction. We now have 3 star systems, where we have a planet that orbits a double star. And this was something that was often thought by astronomers to be impossible. And you remember again from science fiction, this is Luke Skywalker, who grew up on a planet with a double star. The nice people from Lucasfilms allowed us to use these pictures and modify them slightly. So the first planet we saw that reminds us of this, we've had one of our artists change it a little bit to show what living on that planet would be like, although we don't think that planet is very likely because its temperature is about minus 100 centigrade. Now, how would we find life on another planet? The way we think we can do this in the next 10 or 20 years is to look at the atmospheres of these planets. In our own solar system, we find the atmospheres of the planets most like Earth, Mars, and Venus are mostly carbon dioxide. We believe this is the primordial atmosphere, an atmosphere that when a planet formed out of gas and dust in the early solar system would have an atmosphere like that. The Earth's atmosphere is not mostly carbon dioxide. It is mostly nitrogen and oxygen. So one of the things to remember is there are 2 things that we would look for that we would find is evidence of Earth-type life. The first is water, and the second is a gas like oxygen that does not exist in free form without some process, some life process that maintains it. If you looked at the Earth's atmosphere, its spectrum, you would see evidence of water and oxygen. This is the type of spectrum that we think we might be able to get in 10 or 20 years of planets like the Earth around nearby stars. One way one can do this is if we have good enough data is one of these planets passes in front of its star, you can get a spectrum of it. So one of our challenges is to build instruments that are possible to discover planets nearby. Kepler is only looking at planets at very great distance around some nearby stars and try to get their spectrum. We then think our next great astronomy mission, the James Webb Space Telescope, could observe those stars and potentially find a planet with water and oxygen. As these planets transit, you would be able to build up this sort of spectrum. There is a small satellite, and I want to emphasize that one of the key things in the future is to build small satellites to do very good observations. This is a mission that has been not yet chosen for flight, but has been chosen for Phase A. It's called the Transiting Exoplanet Survey Satellite. It would hopefully go up later this decade. And it could find transiting planets around nearby stars that we could then focus the James Webb Space Telescope on. So we could, perhaps by the end of this decade, find evidence of life-bearing planets around nearby stars. To find a lot of them, however, would require a next-generation telescope. You saw one concept of using multiple telescopes. Another one is to use a very large single telescope. This is a concept that could be flown in the 2020s that could directly image some of these exoplanets and again see if they have life. Now, we may find, as we search the universe, no evidence of life other than on Earth. And this is what I want to talk the remainder of my discussion about, is that even if there is no other life in the universe, there is life here. And we believe that in the next half century or so, human life and our life will expand into the solar system and perhaps beyond. Now again, I go back to science fiction. Many science fiction authors have talked about Mars as being a place that sometime later this century could have large-scale human habitations. And I want to talk a little bit about that because I think that is true. Indeed, U.S. policy says that our primary target for human exploration for this reason is the planet Mars. Now, there's a key question, however. What if we get to Mars and find there's already life there? Indeed, about a decade ago, a meteorite, a piece of space stuff, was found in Antarctica that we are pretty sure came from Mars. We looked inside it, and we saw little structures that some people thought could be fossils of bacteria. Now, we now believe this is incorrect. That's one of the other nice things about science. We argue about it. But we may find when we get to Mars that there is life there. Now, this is a very interesting question. Would humans be allowed to go to Mars if there's life there? And if you look at it from a political standpoint, and I apologize for being political, but one always has to be, this is a question that if you happen to be a right-wing person, you are concerned that this life may kill us. If you are a left-wing person, you're concerned that we may kill it. So if we go to Mars and find life there, there may be quite an argument about sending humans there. But there are other places in the solar system that humans could also live. This is the moon. We now know that at the poles of the moon are substantial quantities of water and other volatiles, the chemicals of which life is made. So we could perhaps settle there and have large-scale habitations on the moon. Indeed, this has been discussed quite extensively as one location where humans could establish large-scale first research bases and then eventually settlements. Other locations that are fairly nearby that are very interesting are asteroids. We now know that the solar system has millions of asteroids. Indeed, some of them we're worried about hitting the Earth. The dinosaurs were destroyed 65 million years ago by probably an asteroid impact. Asteroids are very interesting because they have, some of them are made of pure platinum group metals, so are those that want to industrialize space. Others are made of almost pure ice. So asteroids have become very interesting. Indeed, our policy is that our next human target, sometime in the 2020s, that we will send humans to visit a near-Earth asteroid. So this is a very exciting possibility as well. And there are even people that think we could bring one of these asteroids into Earth orbit, perhaps enclose it, and have people and other life living there. So asteroids are a very exciting possibility. Now, I have to mention more science fiction, because the question is, when you put life on other worlds, is it necessarily human life? There's a lot of research into artificial intelligence and artificial life. Some people regard this as a very good thing, but there are other concepts that this could be a very bad thing. There were various movies like Terminator that suggested artificial life might be hostile. So this is an interesting possibility. I also mentioned already synthetic biology, the ability to program life. Indeed, NASA believes that this could be the key to living on another world, where we could program bacteria to extract critical elements in material like oxygen and water from the material we find there. So we've begun a small program at NASA called the Synthetic Biology Initiative to see if we can engineer life to help us live off this planet. And indeed, life is very powerful. A very tiny bit of life, the DNA, for example, what you find in a seed, can produce some of the largest living things on Earth. This has led people to believe that we may be able to engineer plants that would operate on another planet to build us a house or a place that you can live. So this is all very exciting and interesting potential possibilities. We know that the raw materials, as I said, that we can find at the poles of the moon are exactly what we would need to construct life of various types. These are results that we had from a probe several years ago that we crashed on the poles of the moon, the Lunar Crater Observing and Sensing Satellite. In fact, I have to tell a story about that. This was one of my probes from NASA Ames. It took the upper stage of the rocket and it arranged for it to impact into the one of these craters and produce an explosion that we were able to measure that there was water there. Now, as was mentioned, I'm a retired Air Force officer. So at the final readiness review, we have what's called a readiness survey. So they ask each person, are they ready to go? And so they ask the launch vehicle leader, is he ready to go? And he says go, and they ask the range, and they go around the table. Now, this was the first time I was allowed to sit at the big table, and they got to the Goddard Space Flight Center that had the Lunar Reconnaissance Orbiter, and they said go. And they got to me and said Ames Research Center, and I said Ames is go for the first precision bombing run on the moon. And I made a mistake, though. I put that on Twitter. And what I found out was that various people had read my Twitter, and they concluded that since I was a former Air Force officer, that and some astronauts in the Apollo program claimed they might have seen aliens around the moon, that the CIA had discovered an alien base and we were going to bomb it and start an interstellar war. And unfortunately, people got my email address, so I got hundreds of emails from people that said, I'm a mother, I have children, please don't start an interstellar war, we want them to grow up. But I will say we did a pretty good job. We hit within 100 meters. That's pretty good for precision bombing at 300,000 kilometers. But indeed, it was a very successful mission, and we are finding that the material that can support life does exist. Now, this is one of the more interesting life forms. This is called cyanobacteria. It may be one of the earliest life forms that emerged on Earth billions of years ago. It is interesting because it's able to convert sunlight, water, and a few other materials like we find on the moon into oxygen and organic material. We think that one of the things we will take to other worlds is cyanobacteria that can be engineered to produce food. Indeed, already cyanobacteria can produce various food forms like spirulina, which is a food supplement. We think we could engineer it to produce very complete foods. So it's a very interesting possibility. If we can figure out how to actually program the genome, we could transmit, whether you're at the moon or Mars or some other place, the genetic code and actually print out the things one needed to produce pharmaceuticals or extract material or clean the environment. So a very interesting and very exciting future, we think, comes from biology. Now, these exotic concepts I talked to you about of very rapidly growing technology are sometimes called the singularity. In the next 20 or 30 years, it is predicted that we will be able to create computers and engineer biology to the same level of sophistication as the human brain. And as the President Perez said, this is one of the other great mysteries. This is an exponentially growing capability. There are people that believe that sometime in the middle of the century we will reach what is called a singularity, where the accelerated ability of us to do technology goes vertical and creates a very strange and interesting new future. I think this is a very interesting concept, and I'm very proud to say that there is a privately funded institute at the Ames Research Center that is studying this. Indeed, We are particularly delighted that Rona Ramon has sent a number of Israeli scientists to come and study this concept. This may be indeed one of the more important thoughts for the future, not just for our ability to expand into space, but our ability to make life better on Earth. Now, NASA itself, we are trying to build the technology and the stepping stones that enable us to get into space in a big way, into eventually even settle the solar system. I won't go into these details, but this is the process that's ongoing now to build technology to get between worlds quicker, to live in other worlds such as synthetic biology, and to explore those places. As I mentioned, we would hope sometime in the 2030s to actually have a human exploration mission to Mars that could set up a short-term outpost. We are on track to do this. Our primary efforts, as I said, in addition to technology, we are building large rockets that can take us deep into space, the Space Launch System and the Orion capsule, and we are going to turn over access to low Earth orbit to the private sector. And I'd like to close with a few discussions about the private sector. We believe that space will become a true part of all of our lives once entrepreneurship and commercial applications occur in space. And we're already seeing those. Soon you'll be able to buy a ticket for a short ride in space on companies such as Virgin Galactic. Other companies such as Space Exploration Technologies, who I think you'll hear from later in this conference, have already demonstrated that a commercial rocket with a human-carrying capsule can go to space. So this is a very exciting future. We are seeing private groups go to the moon and to plan commercially to send missions to the moon. Indeed, I was delighted that a group of mostly young people here in Israel are planning to send a probe to the moon to win the Google Lunar X Prize, which is a commercial prize. Although I noticed it wasn't all young people. President Perez was part of that, so we're quite proud of that.